Hello everybody, this video clip is the second video clip for chapter 1 of Calculus for Business 2. Okay, previously what we have done is that we introduced the so-called matrix, okay, and the matrix depends on the number of rows and the number of columns, okay. It is the arrangement of usually numbers, okay, in terms of array of row and column. So if the most important thing is that if we have your matrix A, okay, with the sides m by p, and the matrix B with the sides p by n, so this one, it means that your A got p columns and your B got p rows, okay. If they are the same like this, then you can define a matrix multiplication, okay. And the matrix multiplication, usually it is the row multiply a column, okay. By row and a column, it means that if you want to do the multiplication, you need to multiply the first one, okay, of that row with the first one of that column, the second with the second, the third with the third, and then after that you are going to do the addition, okay. And this one will be the first row and the first column. That will be your this position here, the first row and the first column of your resultant matrix, okay, which we will call the C, okay, which we will call the C. And this C, later on, after you do all the multiplication, then the size or the order of the C depends on this M and this n from your A and your B together. That will be the size or the order of your C, the result of the multiplication. So today we are going to use the multiplication of the matrix, okay, as one of the two to solve the so-called system of linear equation. So to do that, usually we are going to do a multiplication like this, okay. Here is your A, okay, for example, it can be like 4 columns, and there is your B, okay, and your B contains only 1 column like this, and then it can be like n rows, okay. So this one, for example, this is a 4, and this one must be m by n, okay, so that they are the same, but then the result will be m by 1, okay, m by 1, something like that, okay. So this one, all right, here is the so-called linear system of linear equation, okay, system of linear equation. By system, it means that you have like several equations together. By linear, it means that each and every variable contains only power of 1, okay, and you don't have like this kind of term, the multiplication term, okay, or you don't have this kind of e to the x term or like y over x term like that, okay. If you have this kind of term, then it's not linear, okay. So the linear equation usually look like this. This one has 2 equations together, okay. And if you look at it this way, here is a coefficient of your x, okay. You are going to collect it as your first column. There is a coefficient of your y. You can collect it as your this one including a negative as well, so you can collect it as your second column, and you are going to multiply with a column matrix, okay, or sometimes we call vector, okay, a column matrix xy, okay. And because on the other side, okay, you got the constant 5 and 9, so the constant will come here on the right hand side, okay. And if you look at the way we multiply a matrix, okay, this is the row multiplied by a column, right? So it means that your 3 will multiply with x, your 1 will multiply with y, and then you add them up, so you have 3x plus y equals to the right hand side, which is 5. So this one corresponds to your first equation right here. Okay. On the other hand, if you look at your second row, 2 and negative 4, your 2 multiplied with x, your negative 4 multiplied with y, and then you add them up. So you got 2x minus 4y equals to what? Equals to a 9 on your right hand side. And then this one actually, it is the same as your second equation. Okay, it is the same as your second equation, just like that. Okay. I mean, if you want, then you can switch a little bit. For example, you may say that, hey, this is the coefficient for the y, this is the coefficient for the x, and then this one you need to, you see, you switch the order of your x and your y, all right, right here. But then your right hand side still 5 and 9 as previously, because this one, your y multiplied with 1, your x multiplied with 3, you add them up, so you got y and 3x equals to 5, which is the same as your, again, first equation. Okay, so however, usually we usually use this kind of form, you know, we go by x first and then follow by y, just like that. Okay, or I mean, you can have this kind of strange situation. Okay, and usually this is not the case when you do during your high school. So this one, you got, you know, 3 variables, okay, x, y, z, but then you have only 2 equations. Okay, the first one is x minus 2y and 4z equals to 3. The second one is 3x minus 5z equals to 8. So you just do the same thing. Okay, so the first column is your coefficient for the x, which is 1 and 3. Your second column is a coefficient for the y, okay, but this one on your second equation you has no y, so it means that the coefficient with the y is 0, so you have negative 2 and 0. And on the z, okay, the last column, you got 4 and negative 5 for the z. And then this one, your column matrix will be x, y, and z, just like that. Okay, as this order. And then your right hand side, it is the first coefficient for the first equation, the second coefficient for your second equation. Okay, so this one here usually we call the coefficient matrix, okay, because it is a matrix that collect all coefficient of your equation. This one is called a variable matrix, and this one is called a constant matrix because it contains only the constant on the right hand side. Okay, so usually your coefficient matrix will refer with the capital A variable matrix will refer to as a capital X, or sometimes it's a small x, depends on the book. Okay, sometimes it is just like that, and then your B, because it is a seems look like a vector because it contains only one column. Okay, so we some of the book may use the small b with the vector notation indicate like that. Okay, but this one we are going to use capital B, just like this. Okay, however, I mean, if it is not that confusing, okay, or if it has no confusing at all about your variable x, y, z, sometimes, okay, sometimes we are going to omit this x, y, z. Okay, it's look like that. Okay, everybody know that these coefficient depends on the variable x, y, z here. So it just means that we can ignore this one and then just put your coefficient matrix and attached with your constant matrix. Okay, and you have this vertical line, okay, to separate between the coefficient and the constant matrix. Okay, and ignore the variable matrix. This kind of notation is called the augmented matrix. Okay, and usually as we continue, we are going to look at this augmented matrix, okay, very often, right? Okay, so how can we solve for this kind of thing, even though you are not that familiar with, but we still try to solve it, okay? Usually to solve it, we are going to get rid of some of the variable, is it? Okay, so by get rid of it, usually we need to have the same coefficient, okay, of each of the of the variable that you need to get rid of. For example, you may see that, hey, the first equation you have a single x, but your second equation you got 3x, okay? So in order to get rid of, or sometimes we call eliminate your variable x, okay, you are going to multiply your first equation, the whole thing on the both on the left hand side and on the right hand side by 3. So if you multiply it by 3, the first one becomes 3x, the second one is negative 6y, the fourth one, the third one is 4 and 3, which is 12z. And then don't forget, on your right hand side you also multiply 3 by 3, you got a 9, okay? So after you have this, then it means that you can just it depends on what you like, okay? This one, if we use your second equation first, multiply, okay, multiply by if we let me do it this way, okay? If we look at this one, okay, first your first equation, okay, subtracted by your second equation, so the first one subtracted by your second one here, okay, what will happen? So it means that you got 3x minus 6y and 12z, okay, and then minus by 3x minus 5z, okay. So this one on your left hand side, the first one here equals to 9, and the second one here on your left hand side equals to 8, okay. So what you end up with is that your 3x and 3x cancelled, and you got negative 6y, you have 12z plus 5z, you see the plus, okay. So you have a 17z, and then 9 minus 8, which is 1, so you have 1 here on your right hand side, okay. So this means that you change your first equation, okay, you change your first equation by using your first equation minus your second equation, and then your second equation remain the same, okay, your second equation remain the same. So can you see what is it in common between these two? You see that the common thing between these two equations is the variable z. So it means that you can solve y in terms of z. You can also solve x in terms of z. So the first one, your y becomes like 1, okay, negative 6y is 1 minus 17z. So you are going to divide by negative 6, so you have 1 minus 17z over negative 6. So the negative will distribute to the one on the top, so you have y equals to 17z minus 1. And on the other hand, if you look at your second equation, so you have 3x equals to 8 plus 5z, and your x becomes 8 plus 5z over 3, or you just usually you are going to write the variable first and then plus the 8 and then divided by 3. So how about your z? Your z has no restriction, so it means that your z can be any real number that you can think of, okay. For example, if your z is 0, then your x immediately it is 8 over 3, your y immediately it is negative 1 over 6. If your z is 1, then immediately your x, it is 13 over 3, your y, it is 16 over 6, okay, something like that. So what does this mean? It means that you have infinitely many solution, okay, infinitely many solution of your x, y, and z, okay, infinitely many solution of, you know, x, y, and z, the triple x, y, z, okay, depends on the value of z, okay. As you change the value of z, your x and your y change, okay. So this one is one of the things that you may need to notice, that hey, we got two equations, okay, but three unknowns, okay, but three unknowns. How about this one? This one is the one that you may very familiar with, okay. You got three equations, 1, 2, and 3, and you also have three unknowns, okay, depends on x, y, and z, okay. So the first one, if you add them up, you got a 2. Your second one, if your x added twice of the y and 4 times z, it is 6. And if your x again add by 3y and also add more by 9z, you got a 12, okay. So you are going to solve for x, y, and z, okay. Again, you may see immediately that hey, you got the same x, okay, in each and every equations, okay, in each and every equation. So it means that you may be able to eliminate the x on each one of them, okay, on each one of them. So let us do it this way. For the equation number 2, you are going to make change by using your number 2 minus your number 1, okay. So your number 2 on your left hand side, it is x and 2y and 4z, okay, and 4z. This is your number 2. Your number 1 on your left hand side, it is x and y and z. And on your right hand side, your number 2, it is 6. Your number 1, it is 2, okay. So here you just adjust it in the same position. You see this is your second equation, this is your first equation, and then you connect it by subtraction, you see. So here you can see that your x and your x cancelled. Your 2y minus y, you got a single y. Your 4z minus a z, so you got a 3z. And then it is equals to 6 minus 2, which is a 4, okay. On the other hand, if you look at number 3, and then you change your number 3 by, again, using your number 3 minus the first equation. So you have your left hand side for your third equation, subtract your left hand side on your first equation, it is equals to your right hand side of the third and the right hand side of your first equation. So again, the x cancelled, the y becomes what, 3y minus y, so you have a 2y, and here 9z minus z, you have 8z, and then the 12 minus 2, you got a 10, okay. Okay, so this is your new first equation, the second equation, and the third equation, the new one, okay, the new one. And then you may notice that hey, at this point, okay, these two equations contains only two unknowns, y and z, you see, only two unknowns, y and z. So why don't we get rid of either y or z of these two equations first, okay, and then after you got one of them, then you may solve for the others, okay. So for example, this one you may think of it this way. You may say that hey, we are going to multiply by 2 first, so you got 2y, 6z equals to 8, Okay, this is your new number 2, and then your new number 2 now it has a 2y, the same as your number 3 over there. Okay, so what we need to do is to change number 3 by using number 3 minus number 2. So your number 3 on your left hand side, it is 2z and 2y and 8z. The number 2 on your left hand side, you have 2y and 6z. And then on your right hand side, number 3 it is 10, number 2 it is 8. So again, all the y's cancelled. Okay, and then you got a 2z equals to 2. Okay, so later on, so you can just put it right there, your 2z equals to 2. Okay, your second equation is still there. Okay, but you don't really need to change it, right? Because this one, the one that you multiply by 2, because you need to get rid of the 2y in the third equation, is it? Okay, so this one is your original second equation. Okay, however, if you look at it one more time, you may see that, hey, on the first one you have the y, on the second one you also got the single y. So it means that if you do a subtraction between the first and the second, you may be able to get rid of one of the y, is it? So you can do, by changing number 1 here, using number 2 first, subtract the equation number 1. So your left hand side on number 2, it is y plus 3z. Your left hand side on number 1, it is x, y, z together. And your right hand side, you have 4 and 2. So again, all the y's cancelled, but you still have something left over. For example, negative x and 2z, you see, because here is 3z minus z equals to 2. And you may say that, hey, it is the same as what? You multiply by negative 1 again. Okay, it is the same as x minus 2z equals to negative 2. Okay, equals to negative 2. All right, so after that, this one contain only single variable or single unknown. So you just divide both sides by 2 to get your z equals to 1. Okay, after you have your z equals to 1, then you can just plug in your z into your second equation, and your so you have y and 3 equals to 4. So you immediately obtain your y as 1 as well. And if your z equals to 1, plug it into your first equation. So you got x minus 2 equals to negative 2, and then you move it there, so you have your x equals to 0. Okay, so this one, the solution of your system of equation that is given, it is x, y, z equals to 0, 1, 1, which is a unique or a single solution. Okay, so it's not the same as what we have on the previous example. Previous one, you got infinitely many solution, depends on the value of z, but this one you have only a single or a unique solution. Okay, x, y, z equals to 0, 1, 1. Okay, and this one, your variable has 3 variables. Okay, it is the same as a number of equation that you have also 3 equations. Okay, now if you keep doing it like this, okay, if you keep doing it like the example that we just gave, it sometimes may get confusing if your equation has, if you have several more equations than the 3 equations. Okay, and if all the numbers involved, okay, it's not that easy like this. If it if it is involved like several fractions and all that kind of thing, then we are going to introduce you some kind of operation, okay, that we are going to usually use it, okay, in order to help you solving the system of equation, I mean systematically, okay, so that it will has a step by steps doing it, okay. This one is so called the elementary row operations, okay, and you got three kinds of the row operations. The first one is the interchanging of the two row. So usually we are write as Ri interchange with Rj, so we use this kind of two-sided arrows like that. The second one is to multiply the whole row by a non-zero scalar k, okay, so don't forget that this k is not a zero, and then you just multiply the whole row Ri, okay, by your k. So sometimes this one it is written as your Ri becomes Kri, okay, so that it will be not that confusing, like which row that it changed, okay. And the third one is that you are going to adding a multiple, okay, a multiple of one row. So this multiple is also a k multiply, and this k is not a zero, okay. So you are going to multiply your one of the whole row by k, so that row is Ri to a matrix, okay, and you are going to add it to another row, so another row is Rj, okay. So usually we are going to write it as the one that we change. For example, we change your Rj by your Rj plus the k times Ri, okay. So usually we are going to write this way, so that we indicate which row that is changed, okay. So for example, what we have done before, okay, what we have done before with that previous example, we can represent it in terms of the row operation, So for example, this one, what is it that you do? Let me just go back a little bit. What is it that we do first over here? Okay, we do the we change the second row by using the second row minus the first row, right? So here, this is what we have done. You see, the second equation minus by the first equation, right? And this one as well, the third equation minus by the first equation. This is what we have changed, is it? Okay, but this one remained the same. So here is the row, the whole equation that remained the same. These two are the one that has changed, okay, by here, I mean these two operations, row operations, right? And then after that we keep this second row, okay, we keep this second equation, okay, still just copy it, all right. And then we change your first equation by do a subtraction, right? Okay, so we use your R1 subtracted by R2, so you have this one here. But for this one you need to multiply by 2 first, okay. So you're going to have a 2 multiply the whole row first, and then you do a subtraction. So it means that your R3, it is subtracted by twice of your R2, and here's the result. And then, I mean, to get rid of some of your coefficient in front of a single variable like this, you are going to change your third row by divided by 2, or it is multiplied by 1/2, okay. So this is what you end up with, z equals to 1, okay. Then to obtain your y, actually I mean, if you do it, you're saying that you replace your z by 1, but what you can do is that if you multiply by 3 and then you do a subtraction again, the 3z and the 3z can cancel, right? So it means that you actually change your second row. Okay, actually you change your second row by eliminate the z. Okay, eliminate the z in your second row. Okay, how to eliminate? You are going to use your second row subtracted by 3 times of your third row, you see, so that this one will has the 3z to eliminate. What if you need to eliminate this negative 2z? Okay, so you are going to use this one again, but now to eliminate you need a 2, right? Or actually a negative 2, so that after you do a subtraction, then this one and this one cancelled. Okay, so it means that you are going to change your R1 by added twice of your R3. Okay, the twice of your third row. So this one, the 2z and the negative 2z eliminate. Okay, so what you end up with is your x alone. So now, I mean, if you can remember, you are going to have your x equals to 0, your y equals to 1, and your z equals to 1. And this one was your coefficient for the x on each of the equation. Okay, it is 1 0 0. The coefficient for your y on each equation, it is 0 1 0, and the coefficient of your z in each of the equation, it is 0 0 1, and on your right hand side it is 0 1 1. Okay, this kind of matrix is so-called a reduced matrix. Okay, and if you notice again, okay, the first thing that you do, okay, this one, the first step that you do, let me use it as this. The first step that you do, the variable that you try to eliminate is your x. The second step that you do is right here. The variable that you try to eliminate now is your y. And the third step that you do here, the variable that you now try to eliminate is your z. Okay, and for the first one, the thing that you will keep is your first x. For your second step, the thing that you keep is your second y. And for your last step, the thing that you are going to keep is your third z. Okay, and the rest you are going to eliminate or get rid of it. Very good. So this is the kind of idea that we have. So let us go into a detail, okay, of a reduced matrix. So a reduced matrix, okay, has some of the condition in order to call this kind of name. Okay, first it says that if a row, okay, does not contain entirely 0, okay, so it means that if a row has like some of the numbers, okay, then the first non-zero entry in the row is called the leading entry. It has to be 1. Okay, so for example, this row, this is the first row. Okay, this one contains some other numbers rather than 0. Okay, so the first non-zero term that you can see must be 1. Okay, in order to be a reduced matrix, the first non-zero term that you see on the row which is not entirely 0 must be 1. Okay, this one is called a leading entry. Okay, this one is a leading entry, must be 1. Where the other entry, so okay, all the other entries in the column in which 1 appear must be 0. So it means that the rest here, okay, under that 1 must be 0. You look at this one more time. Your second non-zero row. Okay, the first one that you see, I mean, when we talk about the first one, it means that the first one from your left. Okay, so the first one that is not 0, it must be 1 again. Okay, but then rather than that 1, it must be all 0. Okay, on top, and the one above it and the one below it must be 0. Okay, and but we don't really care the one that is not a leading. Okay, so this is the leading that we need the above and below to be 0. This one is not a leading, right? So it can be, any numbers, okay, rather than 0 above and below them. Are we good? Look at the third row. Okay, where's the leading? So this one is 0, 0. Here is non-zero, so this one is the leading on this row, and the leading, the first leading that you see, it is number 1, so this is okay. And then the rest, okay, other position in this column rather than this leading, they are all 0. Are we good? This is not a leading, so it can contain some other thing that is not 0. It is okay, this one. Are we good? The second condition in order to call that this one is a reduced matrix is that the first non-zero entry in each row is to the right of the first non-zero entry in each row above it. So it means that if you see 1 here, you are going to see the next one on your right, the next one of the each row on your right. Okay, we get. So for example, this one, it look like this. Okay, and sometimes you may see that, hey, it look like a step matrix like this. Okay, so it's going to have something like a step like that. And any row that consists of entirely 0 must be at the bottom of the matrix. Okay, so you got 3 conditions in order to be a reduced matrix. So let's see whether this one is the reduced or not. Okay, so look at the first one. Here is a non-zero row, right? Here is a leading. Is it 1? Yes. And this one, the rest of the leading, it is 0. There is the second non-zero row, right? Here is the leading for the second row, but it is not 1. So this one is not reduced. Why is that? Because your second leading is not 1. We okay? All right. How about this one? Here is a non-zero row. There is your leading. So your leading is 1, and the rest in that column, it is 0. So it is okay. How about this one? This is non-zero row again. Here's the leading of the second row. It is 1, okay. But then the rest, okay, in that column must be 0. This one is not. Then again, this is not a reduced matrix. Why is that? Because this one, it is in the same column of your second, the leading of your second row, but this one is not 0, so this is not a reduced. Okay, how about here? This one is your first non-zero row. The leading, okay, on this row, it is what? It is 1, so it's okay, and the rest, it is 0. Here, the second non-zero row, okay, the leading is 1, and the rest in that column, it is all 0, so it is okay. However, the one that you appear on the first row, appear to the right of this one on your second row. Okay, this is not the case of your reduced matrix. So this one again, it not reduced because you can say that this one appears on the left, okay, of your first row. How about this one? Here is your non-zero row. Your first or the leading is 1. The rest in that column is 0, so it's okay. Here is your second non-zero. The first leading is not 1, so this one is not okay. So here is not reduced. Again, because your leading on your second row is not 1. Alright. There it is all 0. There it is all 0. There's no 1. So this one is already reduced, okay? Because if you have 1, then you need it. I mean, if you got non-zero, then it need to follow all the properties. But this one you have all 0, okay? So it is okay at the first place. All right. Now let's look at this one. Here is your first non-zero row. Okay, the leading is 1. The rest is 0. You see in that column. Here is your second row, second non-zero row. The leading is right here. Okay, the first non-zero term, and it is 1, so it's okay. And the rest in that column, it is 0. And your leading, okay, of the first row, it is on your left of the leading of your next one. So it look like this. Okay, it's look like this. So it is already a reduced matrix. Okay, so this one is reduced. Okay, even though here is not a 1, it is still okay. How about this one? Your first non-zero, this is your leading, the rest are 0, so it's okay. This is your second non-zero row. Here is your leading is 1, and the rest outside it is 0, and your 1 in the the right from the previous row. So this one it is reduced again. Okay. How about this one? Here it is 1 and all 0. There it is 1 and all 0. And actually it is on the right of each other. But you have this entire 0 row. It must be at the bottom. So this one is not reduced. Why is that? Because of this row not at the bottom. Okay. How about this last one? This one is the first non-zero row. Here is the leading, it is 1. The rest it is 0, so it's okay. Here's the second non-zero row. There is 1, but the rest is not that 0. So here it is not 0, so it is not reduced. Okay, right? So here, I mean, you may need to look at this example again to see whether which one is reduced, which one is not. Okay, and what we are going to do is try to make change of the matrix, okay, into a reduced matrix, okay, or we sometimes call a matrix reduction by using the elementary operation. Okay, so first of all, if you have given this matrix, okay, with 0 like this, okay, 0 0 1 2, and 3 negative 6 3 negative 3 0, and 6 negative 12 2 11. This is given. So what you usually need to do, okay, you really need to have the look at each column first, okay, from your left to your right, okay, and usually the first position of your first column must be non-zero if you can, okay, must be non-zero if you can. So I mean at the beginning you got a 0 here, so you need to switch your row, okay, either using your second or your third, okay, with your first row, so that the first position of your first column is not 0. So what we decide to do is that we are going to do your R1 switch with the R2, okay, interchange. So the whole R1 is right here, okay, switch with your whole R2, okay. So I mean when you consider, you look at it as a column, but when you do operation, you are going to do the operation in terms of row, okay. After that, the first non-zero, okay, on your first column must be 1, okay, it must be 1. So in order to make it to be 1, you are going to divide by, you know, just 1 over this number here. So you have 1 over 3 as a result. So after you divide it by 3, so you have a 1 here, you got a negative 2, and you got a negative 1 and also 0. Okay, but the rest, they just leave it as it is. After that, you are going to look at the one below that leading, right? So here it looks like a leading, but the one below the leading must be all 0. You already have a 0 at your second row, but this one is not. So you are going to get rid of this 6. So how to get rid of the 6? Okay, so you just keep your third row, okay, as it is, but then because here it is a 1, so if you have a 1 here, then you can change your 1 into any numbers by multiply by that number, right? But you need to get rid of 6. You are going to multiply by the what? By the opposite number of 6, which is negative 6, okay. So you are going to multiply negative 6 to your R1, and then you just add with your R3. So the negative 6 R1, it is negative 6, right? 12, okay, because it is negative, it is 6, and it is 0. And you add them up, okay, as you add them up, the 6 and the 6 cancel, so you get, I mean the negative 6 and the 6 cancel, so you get 0. 12 and negative 12 cancel. The 6 and the 2, you have 8, and the 0 and the 11, you got 11. You see, so you using this one together with this one, just add them up, all right, and then your first row and your second row unchanged. The only change is this one. Now what is it that we are going to do? Okay, as we tells you that we are going to sweep by column, right? So the first column is already done. So you look at the second column, okay, and you look at the second element on your second column. It is 0, and then the one below, it is all 0. So it means that you don't need to do anything for this column. So you sweep to the third column. However, I mean, if your second column cannot do anything, you still need to keep your second position of your third column. So now your second position on your third column, it is 1, okay, so you don't need to switch anything, right? If it is 0, then you need to look at the one below whether you can switch the non-zero to this position or not. But this one happened to be 1, so you can keep it as 1, okay, and then you are going to get rid of the rest in that column, okay. So how are we going to get rid of -1? So you just again change your, so we can say it like this, that we are going to change your R1 into your R1 and -1 R2, I'm sorry, not -1, the opposite number of -1, which is 1 R2, and then your R3 can be changed by R3, and then use your R2 as a base, and then the opposite numbers of your 8, which is -8. Okay, so so this is what we are going to do. We are going to do the R2 plus R1. You see, the R2 plus R1. So your R2 remain the same, okay, and your R1, okay, you add them up, so you have a 1, you add them up, you have a -2, you add this one, of course you got 0, you add a 2 and a 0, so you have a 2. But then for your third row, you need to multiply your second one by 8 first. So if you multiply by 8, so you have 0, 0, 8, I'm sorry, -8, 0, 0, -8, and -16. And then you are going to do the addition, you see, the addition with the -8 times R2. So the 0 and the 0, you have 0 here. The 0 and the 0, you have also a 0 here. -8 and 8, you have a 0 there. And then -16 and +11, you have -5. Okay, so this one is your first leading, remember. Here is your second leading, and then the rest, okay, element in that column, okay, of that leading, they are all 0. Okay, so we already done for the second position of your third column. So we are going to sweep to the of course to the last column, right, the last column. But if you take a look at your last column over here first, okay, and then for the last column, because you just finished your second position, right, on the third column. So by your last column, we are going to look at the last position, the third position here, okay, on this last column. Here is a -5. So in order to this one to be a leading, then you change it into a 1 by divided by -5 or multiplied by -1/5 to your R3. So because the one previous, I mean the one before it, they are all 0. So you have all 0 like that. And then you divide the last one by -5, so you have a 1. And then again, this is your leading, your first leading, your second leading. This one will be your third leading. So in order to make it to be a real leading, then the rest on that column must be 0 again. So what is it that we are going to do? We are going to change your R1 by using your R1 added by an opposite number here. So it is -2 R3, and your R2, you are going to change your R2 by again opposite number here with your R3. Okay, so let's put it this way. When you are taking care of the first position, okay, on your first column, the one that you use is only your R1. Okay, the one that you multiply by the opposite number is your R1. And when you taking care of the second position or the second leading, okay, the second leading of the second row, then the one that you are going to make it change, okay, you are going to depend on your R2. And then for this one, because you talking about your third leading, so the row that you are going to make use of it, it will depends on your third row, your R3. Okay, so this one, you are going to multiply your R3, the third row, by -2, and then you are going to add it with your first row and your second row. So because it is 0, so you add with the first one, it will be the same. It will be the same. It will be 0 again, and negative 2 and 2, it will becomes a 0. Okay, and this one, when you talking about your second row, because they are all 0, so here you got the same thing, but not the last one, because your last one it is a negative 2 and a 2 here, so you have a 0 over there. So here your first leading, your second leading, your third leading, and this one is already a reduced matrix. Okay, so it means that from the one that is given, from the matrix that is given, you can use a series of row operation to change the given into a reduced one. Okay, into a reduced one by using all this kind of operation. Okay, and this is the thing that we are going to use it later on. All right, this is the thing that we are going to use it later on. So we are going to stop this clip right over here, and then we will continue with the make use of this reduced matrix to solve the system of linear equation later. We'll see you then. Bye bye.